Okay. In the last lecture, we studied solution of nonlinear equations, and the way we solve these problems, least square problems, turn out to be very close to these problems, systems of nonlinear equations, in the method of solving. So today we will cover least square problems before going ahead to explore more advanced optimization methods for general problems. So in least square problems, first linear and then nonlinear. So least square problems are in a way simple problems, but they are extremely important in the sense that if the form of the error functions turn out to be very complicated, then even least square problems may become complicated. And more importantly, least square problems happen to be those optimization problems which are faced by the largest number of researchers. Even those researchers whose research is completely experimental and they typically stay away from computational work, even they need this because if they are experimentalists, then they typically try to model phenomena from their experiments, from their observations. Okay, and while modeling an unknown phenomenon, quite often it happens that after a lot of brain racking, you have developed an understanding of the form of the function in which there are some parameters which have to be fixed. Okay, and how to fix that? For that, you have to conduct experiments to get the real truth, okay, from the horse's mouth. So, as you conduct the experiments, the unknown function values and the values of the their independent variable of which this is the function, these are recorded through experimental observation, experimental measurements, and those parameters are still unknown, which you need to determine. And the way to determine that, I mean, there can be several possible ways. The simplest and the most prevalent way is to find out, I mean, from your model with assumed values of the parameters, you can determine the value of the function as it would be if the model and the parameters were correct. And from the experiment, you have another value. So you subtract and get the error. So each data point will give you an error value, which may be positive or negative. You want to eliminate or reduce either of them. Okay, whether positive or negative, you don't like either of them. So you may like to reduce its square for each data point. And so what you do is that you sum up all those squares of errors over all the data points and define this as the master function which you really want to minimize with respect to those parameter values. And finally, the parameter values that you get with those parameter values, which minimizes this error, you evaluate that minimum error value. That is minimum of the sum of squares of errors. Okay. If that turns out to be small, that means that everything has been good. First of all, the form of the function is most probably correct. And then your parameter values, I mean, your experiment has been good, experimental errors are less, and now you have got the correct parameter values also for that. Some error will always remain if the data is realistic, not manufactured. Okay. So then the biggest advantage for the experimental scientist is that it vindicates her hypothesis. Now she knows that the form of the function which I assumed, which I decided upon, is correct. Okay. So this minimization is the least square problem, this minimization problem. So when is the problem linear? When the unknown function is, or for simplicity, is modeled as a linear combination of a few known basis functions. Okay, so as if the unknown function is a contribution of several parts. The form of each contribution is completely known except how much of that goes in the unknown function, the coefficient. Okay, so when it is known as a linear combination or modeled as a linear combination of some basis functions or contributing parts, and their contribution is wanted, how much with how much we need to multiply these basis functions to get the complete unknown function. Okay, so when these coefficients are to be determined, then the dependence of the unknown function on the coefficients is linear, and then you call it a linear least square problem. See how it works. So suppose the unknown function is modeled as a linear combination of these basis functions, psi1, psi2, psi n, and so on. So these are completely known, and x1 times this plus x2 times that, and so on. That sum is the unknown function, and you want to determine the coefficients x1, x2, etc. So this is a linear least square function because here the unknown function depends on the parameters, unknown parameters, in a linear manner. Psi1, psi2 functions can be as nonlinear as they like. You don't mind because you know them. So this is a much simpler problem compared to the general nonlinear least square problem. Okay. So for a measured pair of values ti, zi, the error of the ith point ei will be this thing evaluated at ti, that is here, minus zi. Okay. So since this linear combination, you can also write in a matrix vector form where the column vector of the values of the basis functions, you take transpose and then multiply with x1, x2, that vector. From that, you subtract this observed value, measured value of z, and this is an individual error at the ith data point. Okay. So assemble all these errors, E1, E2, E3, E4, etc. in a column vector. Okay. How many members in that? As many data points you have taken. Okay. Then you get this vector equal to 1 row, 2 row, 3 row, and that many rows. Okay. As many data points you have taken. So that gives you a matrix times x minus z1, z2, z3, z4, that many. Okay. So you have got a system of equations. I mean, not system of equations yet. You have got error as a linear function of the unknown parameters. Okay. Where the matrix A is known from this model, and x you want to determine, and z is known from observation. So these are the errors. Ideally, it would be ideal if this error vector were completely zero, but that is unbelievable because there will be experimental errors. So how less it would be with these experimental measurements? So for that, you minimize the sum of squares of each of these. That is, basically you minimize the norm square of this vector. That one way to write this is this. There is an extra factor of half, which will cancel out as we progress. So you multiply out this, okay, and get this. Now this is a quadratic function of x. Not only that, it is a convex quadratic function because A transpose A is positive semi-definite in the worst case. And typically the worst case does not come up if your design of the experiments or design of the model function, these basis functions have been, I mean, pickup of the basis functions, selection of the basis functions have been good. Basically, if the basis functions are linearly independent as functions. And then the measurements that you have taken that span all the possibilities in a way, that is, it does not leave out one direction of information completely. In that case, A transpose A will be also positive definite. Okay, all eigenvalues will be positive. And that means in that case, it would be not only a convex quadratic function, but it's a strictly convex quadratic function. And in that case, the solution will be directly found from the first order conditions. If you differentiate it and set equal to 0, you get A transpose AX minus A transpose Z. That has to be 0. So you solve this linear system of equations, which you know, and that's the solution. That's X. That's the set of parameter values. After getting that, you work out this function value at the converged value of X. And if that is very small, then you go to publish your findings. That is great modeling. Okay. And to solve this positive definite system, symmetric positive definite system, you can apply the simplest method for linear systems, which is Cholesky decomposition. Okay. So linear least square problems are that simple. And this method on the way gives you also an interesting solution to linear systems in general. Okay. Look at this carefully. A general and computationally efficient framework to solve linear systems Ax equal to Z of all kinds, having the number of equations less, equal, or more than the number of unknowns. Okay. So if there is conflict, it will try to minimize that. If there is indeterminacy, it will try to get you the smallest x that satisfies it. After handling inconsistency, then indeterminacy can arise. In that case also, it will do the same thing. Ill conditioning, singularity, everything you can handle in this framework. So let us study this framework. And when you know that you may have to solve linear systems of all kinds, rectangular, square, well conditioned, ill conditioned, singular, whatever, and in every case you need one working solution. Through this method, you can find in a single framework a working solution for each and every linear system of equations. Okay? So what it does, for any possible conflict in the system, you reject the conflict, minimize the inconsistency, basically minimize a sum of squares. Okay, by pre-multiplying the equation by A transpose and get this. Okay, this gives you the solution, minimizing error norm. Okay, but in the actual least square problem, we said that A transpose A will be positive definite. But in the case of a system of equations, that may or may not be, because we are talking about a general method to solve all systems of equations like this. So in the worst case, A transpose A may be singular. First, it's semi-definite still, but some eigenvalues may be 0. Okay, and it will happen so certainly if A has less equations in more number of unknowns. Okay, if the dimension of X is larger than dimension of Z, in that case it will certainly happen. Okay, and you don't want that. It is a different matter that it will have infinite solutions, but you need only one of them. Okay, and only on the way to that, you don't want to handle singularities, you want to avoid them. Okay, so The resolution is very simple. You add a little number to all the diagonal entries of this. That little number here we have denoted by new square. Okay. It is as if adding a quantity of the magnitude nu to the original matrix. So since it is A transpose A, so it is nu square. Okay. So just add that, but make it small, not too large. Okay, because this nu will actually introduce a little amount of error in the final solution. Okay, and you have to keep nu so small that the error introduced is insignificant. So what this nu is doing, it is like immunization, vaccination. Okay, in order to protect the system from singularity or ill conditioning, which may lead to catastrophic outcome, it is introducing a little error, avoiding all that huge error that would come if you are operating with a singular matrix. Okay, so a little error it will introduce from its side, thereby making the system immune from the actual disastrous problem of singularity. Exactly what vaccinations do. Okay, so it was already positive semi-definite, A transpose A. The worst eigenvalue was possibly 0. When you add nu square to all the eigenvalues will turn out to be certainly positive, at least nu square. Okay, so according to that, you select nu. 0.0001 is a beautiful nu. Okay, in such situations, or 0.01 if your application is rough and you want to avoid ill conditioning by a wider margin. And this is symmetric positive definite. So again, you can happily solve it by Cholesky decomposition. Okay. So in effect, what it does is it minimizes this weighted sum. That is, this part was minimized with the first step itself, and this was always consistent. Okay. And added to that, this part will ensure the singularity avoidance. And as a result, finally, rather than minimizing this, which was your original intention, you will end up minimizing this. You can work out the first order condition for minimality of this function, and you will find that you get this system of equations. Okay. So this much regarding linear least square problems and associated little digression on a general method to solve linear systems of equations. Now we go to our main issue, which is nonlinear least square problems. Now let us take the unknown function zt to be modeled to depend on its parameters in any manner. And therefore, we cannot write a nice expression and we say that say zt is essentially h of t and x. Okay. X has the unknown parameters. Okay. So the error of the data point would be this, and with many such data points, certainly more than the number of parameters that you want to determine, we try to minimize this, right? This was the plan. Now, to how to do that we have actually covered in our earlier discussion in the context of Levenberg-Marquardt method which turns out to be exactly suited to solve this kind of optimization problems. So here in this lecture, we will see an example. Say the function we want to model is of this form. Okay. In which z0, a, xi, omega, phi, these are the parameters we want to determine. And for that, we have collected experimental data, t and z. Okay, 10 values. To determine 5 parameters, we have got 10 values, which is all right. Okay, 20 would be better. Okay. So these 5 parameters, first of all, we represent as x1, x2, x3, x4, x5, and then put this function in the form of a function of scalar t and vector x. Okay, like this. And then the error turns out to be this, and its gradient this. Okay, just differentiate it with respect to the 5 variables, and you have got this gradient. Now, if you have such t equal to t1, t2, t3, t4, capital N of them, in this case 10 of them, and then each of the gradient values, corresponding gradient values, you take the transpose and put as a row, then the assembly gives you the Jacobian of the vector of the vector function E, okay, with respect to x. So this is capital N by small n, that is a tall matrix, 10 rows and only 5 columns. And the corresponding error vector, you have a column of 10 entries. Okay, so this is now minimized by Levenberg-Marquardt method, the formulation that we earlier did. And in this example, we took the initial value of gamma as 100, even 10 works, and update factors 2 and 5, as I told you, as my favorite values. Okay, and I gave maximum number of iterations as 100, to which it did not have to go. Before that, it reached the termination condition, which is tolerance of this. That is, delta E turned out to be less than this within something like 18 iterations. Okay. So we started with this starting point. Why not 0, 0, 0, 0, 0? Why not starting from the origin? The reason is that at origin, since x2 will be 0, apart from others, these 3 will be zeros. Okay. So at the starting point itself, 3 columns of the Jacobian will be totally 0, which is, I mean, something very awkward, and it will be very bad for the health of the method. Okay. So that is why if we had saved just this one from 0, then it would be all right. But how does it matter? So take a starting point, whatever. In fact, the value of the algorithm is high if it can converge to a good solution, to a solution from any starting point. So this turns out to be the values of the parameters, and for that the half of the sum of the squares of the errors turns out to be this, which is very small. Now this leads us to 2 conclusions. One, the total number of iterations is only 18, though 100 was allowed. That means it did have a natural termination. That means post-convergence termination. If it were 101, then, or 100 for that matter, then we would say that perhaps it has not converged and the thing is thrown out. In that case, this also would be a high, of course. Okay, and at the convergence at converged point, the error being so less, that signifies that the model was good. Okay, so these are the two conclusions. This immediately tells that it is a reliable result for X, and then this small value tells us that the model was reliable. Okay. So what we have seen in this particular lecture, first of all, what are least square problems? A tool to help modeling of complicated phenomena, in which you, based on the physics of the problem, based on the subject matter of the problem, you decide on the form of the function, and in order to determine the parameters involved in that properly, you take experiments, and this is a method. Least square problems turn out to be the problems formulated to minimize the error norm of the errors of the experimental result. And for that, we find that for linear least square problem, there is a very straightforward mechanism to solve the problem, which is actually very close to a general formulation for solving linear systems of all kinds. Okay, a general system of linear equations. And for nonlinear least square problems, we studied Levenberg-Marquardt method, which turns out to be just cut out for solving nonlinear least square problems. So having settled these topics of nonlinear equations and nonlinear least square problems, and having utilized the Levenberg-Marquardt method completely, we now go to the advanced set of methods, basically two classes of methods: conjugate direction methods and quasi-neutral methods. So in the next lecture, we'll take up conjugate direction methods. Thank you.